Hundreds of miles above our heads, these incredibly complex, multi-million-dollar satellites are doing work we rely on every single day. But here's the thing. Up there in the vacuum of space, there's no mechanic, there's no repair shop, and you definitely don't get second chances. Just one single component malfunctioning, and poof, that's it. The entire mission can be over, instantly. We're talking about a catastrophic failure that turns a marvel of engineering into just another piece of floating junk. So that leads us to the billion-dollar question, right? If you can't physically get your hands on the hardware, how in the world can you know when it's about to break? Well, that's the mystery we're going to unravel. To solve this, researchers had to zoom in. They focused on one specific and very vulnerable component. You could almost call it the satellite's Achilles heel. This part is called a reaction wheel. Now, what is that? Well, you can think of it like a super precise, high-tech spinning top. By changing how fast this wheel spins, the satellite can pivot and point itself with incredible accuracy. Without these, a satellite is basically just tumbling blind through space. And here's the catch. As brilliant as these wheels are, they are a known weak point. They're a mechanical part in an otherwise electronic world, and, like any mechanical part, they eventually wear out and fail. Now, what makes this problem so incredibly tricky is that the way it fails, the slow degradation, this sort of sickness, is completely invisible. You can't just look at a number and see that it's getting worse. Engineers have a name for this hidden measure, the health index. For our reaction wheel, the key thing to track is the motor torque constant, or KT. You can just think of it as the motor's raw power. As that KT value goes down, the motor is getting weaker, and you know failure is just around the corner. And this slide just lays out the challenge perfectly. On the left, you've got the symptoms, the things ground control can actually see, like data on wheel speed and how much electrical current the motor is drawing. But on the right, you have the actual disease they're trying to find, the motor's health slowly fading away, which they can't see at all. So it's really like being a doctor for a patient in space. You have all the vital signs, all the symptoms, but you have to figure out the underlying disease before it's too late. And what do you do when you have a mystery like that? You bring in a specialist. In this case, a doctor that can see patterns that no human ever could. A highly specialized artificial intelligence. The AI they used is called an LSTM network. That stands for long short-term memory. And the name pretty much says it all. It's an AI with a fantastic memory. It's designed specifically to look at data over long periods of time, like sensor readings from a satellite, and spot those super subtle long-term trends that scream, failure is coming. Okay, so how does this AI doctor actually make its diagnosis? Well, the researchers developed this really clever and elegant solution that breaks the problem down into a three-stage process. This flowchart, taken right from the research paper, is basically our roadmap. It shows us exactly how they get from that raw, confusing sensor data all the way to a final, concrete prediction. Let's walk through it. So it really works in three distinct steps. First up, stage one. The AI learns to predict the future of the symptoms, what the wheel speed and motor current are going to look like down the road. Then, stage two. Another AI model takes those predictions and uses them to estimate the hidden disease, the true health of the motor. And finally, stage three. By tracking how that estimated health is declining, the system makes its final prognosis. It predicts exactly how much useful life the component has left. And check this out. This is the proof in the pudding from that first stage. The solid line is the real data, what actually happened on the satellite. The dotted lines, that's the AI's prediction. I mean, just look at how closely it tracks reality. This level of accuracy is the absolute foundation for everything that comes next. Okay, so we've got an AI that can accurately guess the hidden health of the motor. That brings us to the final and most crucial step, predicting the exact moment of failure. The researchers set a very clear finish line. They decided that a reaction wheel has officially failed when its motor health, that KT value we talked about, drops to just 30% of what it started at. So the AI's job is to plot that declining health curve and calculate the exact moment it's going to cross that critical 30% threshold. So, after all that complex modeling, all that work predicting symptoms and estimating the hidden disease, how accurate was it? It was stunningly accurate. The model predicted the remaining useful life of the component with an accuracy between 97.5 and 99%. For mission-critical work like this, that is an absolute game changer. But this incredible breakthrough isn't really just about satellites. It's basically a blueprint for predicting failure in almost any complex machine you can imagine. Seriously, think about it. This same method, using the symptoms you can see to diagnose a problem you can't, could be applied to almost anything. The jet engine on the next plane you take, the massive wind turbines powering our cities, even critical medical equipment in a hospital. This is a blueprint for being proactive, not reactive, on a massive scale. So yeah, this research is way more than just a clever trick for satellites. It's really a glimpse into a future where those catastrophic, completely unexpected failures could, maybe, become a thing of the past. Which leaves you with a really big question. What could we build? What could we achieve if we knew things weren't going to break?